Welcome back. In the last couple of videos, you may have gotten to the point where you thought to yourself, man, some of this mathematics must be more complicated than it needs to be. After all, a lot of the systems, for example that infinite sheet of charge, have a lot of symmetries, and therefore maybe we could try some trick in order to make the problem a little bit easier for ourselves. Well, today we're going to be talking about a quantity called flux that hopefully will allow us to make some of these problems a little bit easier. But at the center of this idea is a question of whether or not I can find out any information about an object. Say I'm sitting in the middle of a universe. Could I find out what my mass or charge is by probing the space around me and trying to come up with, well, what are the characteristics of the space that surrounds me? And if I do that enough, if I collect enough information about the space around me, can I actually calculate something about what's going on at the center? So the quantity that we're going to use to describe this is something that's called flux. Now, you may have heard this term before, but technically speaking, flux is a mathematical quantity that I'm going to be able to define given a vector field, and it needs to be a vector field, and a surface. If I have these two things, then I can define what flux is. And how you want to think about it is how much of my vector field is actually going through my surface, right? So in this picture, I have a rectangular surface, I have a red vector field, and I can think about, well, what is the total integrated strength of that vector field as it crosses over that surface? An example that you might be familiar with in your everyday life, let's consider a rainstorm, right? This is a great vector field because I have a lot of rain that's coming straight down from the sky, so it's heading down in the minus z direction, and it has some uniform strength that I'm writing here as r naught. So this rainstorm is going to be basically a constant vector field that always points downward. Well, if I now define some surface, maybe my head, and I think about that surface or the cross-sectional area of my head in this rainstorm, I can now think about, well, how wet am I going to get, right? How much of that rain is going to flow through my surface? And you know that you have some control over how wet you're going to get, right? The integrated strength of that vector field across that surface. And there are three ways to change how wet you're going to get. You can make your surface bigger or smaller, right? If I change the cross-sectional area of my surface, I'm going to change how much water, how much integrated field strength I get. I could also make it rain less, right? That is, the strength of the rain is going to tell me how wet am I going to get, right? So these are the two obvious ones. I can make the surface bigger and accept more water, smaller accept less water. I can turn the faucet up, I can turn the faucet down, and that's going to change the strength of the water. But there's another thing that you know about, and that is I can change the orientation of the surface that I'm looking at. And therefore, the relative orientation of my surface and my vector field is going to define how wet I'm getting. And so my definition of flux, which we abbreviate with the capital letter phi, is going to be the integral over my vector field, which I'm writing here generally as f, dotted with my surface, and here I'm talking about dA, I'm talking about an infinitesimal piece of my surface, but I'm integrating the vector field over the surface, but of course I have a dot product which is going to give me information about the relative orientation of my surface with my vector field, right? You remember dot products say, well, if two things are in the same direction, then they're going to be maximized. But if they're perpendicular to each other, then they're going to go to 0, right? And so now I start to realize why that dot product is so important for orientation. Now, there's a special case where I have a constant vector field and an example of this is, of course, something like the rainstorm I was looking at, and a constant area, right, where I have some, maybe a loop or a hat or a body or a head or something, but I have a constant area that I'm not allowed to change. Then my flux, the integral goes away because I'm integrating over something that isn't going to be changing as I move along my surface. And I get that the flux is going to be the magnitude of the vector field, which is of course a constant, times the area of the object that I'm looking for, which is of course a constant, times the cosine of the angle in between the area and the vector field. But wait a second, right? I said the force has a direction. That's something I can understand. How does the area have a direction? Well, if I have a surface, there's actually a direction associated with that surface, and it turns out that it's neither of the directions that you think it is, right? If I have a flat plane, I know that, say, in the xy plane, then I have two directions associated with that plane. Well, neither of those help me, because any linear combination of those two directions is still going to be inside the plane. But there is a unique perpendicular to the plane, and that's the vector that defines the direction of A. And so in this example, where I have two constant vectors, I can see if the force is either parallel or anti-parallel, or if the vector field is either parallel or anti-parallel to my area vector, then I'm going to maximize the amount of flux, either positive or negative, but I'm going to maximize the magnitude of the flux because cosine of 0 is 1. But if I change those relative orientations so that the area is perpendicular to the field, well, that's what that's really saying is that the field isn't flowing through the surface at all, right? Because in order to flow through the surface, there has to be some part of the surface that's perpendicular to the vector field. So let's think about what we can do then with this mathematical structure. Well, if I have a vector field F and a surface A, and I want to actually start to calculate this dot product, which direction should I choose A to be in, right? After all, the force is something that's physical, or the field is something that's physical. In this case, it's pointing downward. Does my area vector point up, or does it point down for this circular surface that I'm drawing? Well, the answer is, it doesn't matter. If I have an open surface, that is, if I have a surface that has a boundary, then it doesn't matter which way I take the area. I have to note it. I have to use it to calculate the flux. But it turns out that if I have an open surface, it doesn't matter which way I calculate the area. On the other hand, though, if I have a closed surface, such as this jelly bean or this box, then the area vector always has to point outward. And that's really important, that if I have a closed surface, then I no longer have the luxury of saying, of being free to open up, to say which way the area vector points. But if I have a closed surface, I have a defined inside and I have a defined outside. And the mathematical formalism that we have defines the area vector to be the outward pointing normal to the surface along any point. Okay, I think it's time for an example. Remember, after all, we're trying to get information about what's inside, right? What's at the center or what's inside something, and all I can do is probe around it. So consider just a charge Q that's inside a spherical shell of radius r And I'm drawing it in 2 dimensions, but this is actually a spherical shell. It's a 2-dimensional globe around in a 3-dimensional space. And I want to calculate what is the electric flux, which means that I'm going to take the integral over my surface of my vector field, which is E dot dA. And since I'm talking about a closed surface, I'm going to add a little circle on the integral sign just to remind myself that this type of flux that I'm calculating, the electric flux, is something that I'm defining on a closed surface. Well, now I can actually do the integral. I have to be a little bit careful because my outward pointing normal, right, is always going to be in the r hat direction, right? It's always going to be pointing outward in spherical polar coordinates. And I also know that a little bit of this area, dA, is going to be given by, well, what's the fractional part of the total surface area? So that the area infinitesimal is r squared sine theta d theta d phi, right? After all, in spherical polar coordinates, the parameterization is over the 2 angles, where I'm using the standard parameterization, where theta is the angle from the z-axis downward, and phi, little phi in this case, is the azimuthal angle. And now that I have that, and I know from the last lecture that the electric field due to a point charge is 1 over 4 pi epsilon naught q over r squared r hat, now I have absolutely everything I need to calculate the flux, right? So the flux is going to be the closed surface integral of E dot dA. Now I have a bunch of constants, right? I have a 1 over 4 pi epsilon naught. I have a q over r squared. Now technically the r squared is evaluated at the surface in question, and therefore it's really a capital R squared because I'm evaluating the field strength on that surface. And then I have r hat dotted with r squared sine theta d theta d phi. And of course, I should take a point off my lecture here because my dA, as I wrote it here, has a vector symbol. So I need a vector symbol over here, and that's an r hat times r hat. And now most of this is, of course, most of these are just constants in terms of vectors, right? I get a little bit of simplification from the r squared. I can pull the q over 4 pi epsilon naught out, and I have this closed surface integral of sine theta d phi r hat dot r hat, right? And so I still have that dot product, but now that dot product is just hitting these 2 unit vectors. Now what's the angle between r hat and r hat? Well, 0. Of course, they're in exactly the same direction. So this dot product turns out to be just 1 because the dot product of 1 times cosine 0 is 1 times 1 times 1, which is 1. I feel like I'm in a Clue movie. And so this whole thing reduces to q over 4 pi epsilon naught times the closed surface integral of sine theta d phi. Now I could do this out, but of course the d phi is going to give us like a 2 pi, and that's going to cancel some of the 4 pi. The sine theta d theta is going to give us a trigonometric identity. But at the end of the day, I get that the flux is equal to q over epsilon naught. And that is to say that how much flux goes through the surface doesn't matter with the size of the surface. If I went further and parameterized the surface in a different way, it also doesn't matter the shape of the surface. In fact, the amount of flux that I calculate on any surface that encloses this charge is going to be equal to the charge divided by epsilon naught. That is to say that the total charge enclosed in any surface is just epsilon naught times the flux. And that's something that's known as Gauss's law. So if I draw any surface in anywhere in the universe, and I integrate the electric field, and I should say in electrostatics, if I integrate the electric field over that surface, and I multiply it by epsilon naught, that's going to tell me how much charge is enclosed in that surface. And that turns out to be an awfully useful mathematical tool when it comes to calculating things in electricity and magnetics.